Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. This is a lecture on determinants. The main points of this lecture are that if you have n by n matrices, then if A is invertible, the determinant is non-zero, and if the determinant is non-zero, then A is invertible. That determinant of AB is determinant of A times determinant of B, and if A is invertible, then the determinant of the inverse of A is 1 over the determinant of A. For the proofs, we will use elementary matrices and their determinants. The background is in earlier videos. I have a video where I define determinants. I have another one where I show that the determinant is multilinear and alternating, and then a video that I show the effects of row operations on determinants. I will remind you of what is needed here, but to get a fuller picture, you should watch the earlier videos. What's the definition of determinant? If an n by n matrix walks through the door and you want to find its determinant, the way I define it, there's other ways to define it, is to find all signed elementary products and add them together. The result is a number, and that's called the determinant of A, and we denote it by dit A. An elementary product is a product of n entries, no two from the same row or the same column. So in your n by n matrix, you pick one element from each row and column and multiply them together. A signed elementary product is an elementary product when you sometimes multiply it by -1. How do you decide that? For each row, there's going to be one entry of your elementary product that's in that row where you record the column of that entry. So in first row, maybe you're in column 3. In second row, maybe you're in column 7. You just write those down, and that gives you a permutation of 1 through n. And if the permutation is odd, then you multiply your elementary product by -1. Otherwise, you don't do anything. Which permutations are odd? The ones where the number of inversions is odd. And an inversion is when a bigger number occurs before a smaller number. The important thing that we need to know, which I proved in a previous lecture, is what happens to a determinant when we do elementary row operations. The elementary row operations are 3 types. You could interchange 2 rows of a matrix, you could multiply a row by a non-zero constant, or replace one row with the sum of that row and a multiple of another row. This is a row that I want to change. I decide what's another row that I like. I multiply that other row by a number and add it to this. I don't change that other row. I only change this row that I'm adding that multiple to. These are called elementary row operations, and we use them, for example, in finding reduced row echelon form of matrices. I have a whole video on elementary row operations. Now, what do elementary row operations do to determinants? If you interchange 2 rows, then the determinant gets multiplied by -1. Again, the proof of these are in the previous video. If you multiply a row by a scalar alpha, then the determinant gets multiplied by alpha. In fact, this scalar doesn't even have to be non-zero, but if you want an elementary row operation, you need to multiply by a non-zero constant. And if you replace one row with the sum of that row and a multiple of another row, the determinant actually does not change. I'm going to give you now a quick proof of why invertibility of a matrix is related to its determinant. So if A is an n by n matrix, I want to prove to you that A is invertible if and only if its determinant is non-zero. The main ingredients I'm going to use are the following. If A is invertible, then it's a row equivalent to the identity matrix. An invertible matrix is an n by n matrix, and it's one where if you do elementary row operations, you get identity. That's what row equivalent means. You do elementary row operations, and you can get this other guy. The proof of this is in another video on conditions for invertibility of matrices. All of these videos are referenced in the notes. If A is not invertible, A is row equivalent to a matrix with at least one row of zeros. And when you do elementary row operations, the determinant gets multiplied by a non-zero constant because either you're switching 2 rows, in that case, you're multiplying by -1. If you're multiplying a row by a non-zero constant, the determinant gets multiplied by that non-zero constant. And if you do the third elementary row operation, the determinant gets multiplied by 1. I know that identity has determinant 1, and a matrix with a row of zeros has determinant 0. For a matrix of rows of zeros, because for every one of those elementary products, you have to use one of the entries in that row, all the contributions will be 0 and the determinant will be 0. So if A is invertible, then it's row equivalent to identity. That means that you can start with identity, do elementary row operations, and get to A. Identity has determinant 1, and every row operations that you do gets the determinant multiplied by non-zero constant. So you take 1 and keep multiplying by non-zero constant. At the end of the day, when you get to A, the determinant of A will also be non-zero. If A is not invertible, then it's a row equivalent to a matrix with a row of zeros. That matrix with row of zeros, its determinant is 0. Now, if you keep doing elementary row operations to that, you're multiplying it by non-zero constants, and that 0 will stay 0. and so the determinant is 0. Now, let's talk about elementary matrices, which is quite different than elementary products in an n by n matrix. If you have an m by m matrix, a square matrix, it's called an elementary matrix if you can get it from the identity matrix by single elementary row operation. So for example, these are some elementary matrices. The first one, I multiplied the second row by alpha. As long as alpha is non-zero, this is an elementary matrix. The second one, I added k times the first row to the second row. In the third one, I switched the two rows. Those are all elementary matrices. I got them from identity by doing just one elementary row operation. What are these elementary matrices good for? If A is an m by n matrix and E is an m by m elementary matrix that came from some elementary row operation, then if you want to do that same elementary row operation to A, you can find E times A. The purpose in life of these elementary matrices is to do elementary row operations for you, and they do that when you pre-multiply them by a matrix. If A is an n by n matrix, A is invertible if and only if it's a product of elementary matrices. That follows because we said that a matrix is invertible if and only if it's row equivalent to identity. If you can start with identity and do elementary row operations and get to A, instead of that, you can say you're multiplying by elementary matrices, and so you have a product of elementary matrices that gives you A. Now, I'm going to talk about what the determinants of elementary matrices are. The determinant of identity is 1, and one row operations on identity gives Z. If you switch two rows, so you start with identity and switch two rows, well, of course, we said that elementary row operation multiplies the determinant by -1. So the determinant of that elementary matrix is -1. If you multiply a row by scalar to get E, the determinant is going to be alpha times 1 is just going to be alpha. If you get E by adding a multiple of one row to the other, the determinant of E, that elementary matrix will be 1 because you started with identity, which had determinant 1, and then when you do this elementary row operation, nothing changes. One corollary is that the determinant of elementary matrix is never 0 because it's either -1, non-zero scalar, or 1. The first thing I want to prove is that if you have an n by n matrix and E is an elementary matrix, then the determinant of EA is the determinant of E times determinant of A. Determinants is multiplicative in this way. There are 3 types of elementary matrices, and that gives us 3 cases. You might have switched 2 rows to get E, in which case EA is A when its 2 rows are switched, and determinant of EA is going to be minus determinant of A. But that's exactly determinant of E times determinant of A, because we said that determinant of E in that case is -1. You might have multiplied one row by alpha to get E. In that case, EA is the matrix A with one of its rows multiplied by alpha. And so the determinant of EA is alpha times determinant of A. But because alpha is also the determinant of E, the determinant of E times the determinant of A is determinant of EA. And in the case where E is the elementary matrix that you got by adding a multiple of one row to another, then determinant of EA and A are the same. And that's again the same as determinant of E times determinant of A because determinant of E is 1. This proof was just the proof of the pudding is in the eating. Just try all 3 types of elementary matrices, and the determinant of EA is the determinant of E times the determinant of A. Now we want to slightly generalize what we just said. If A is an n by n matrix, and I have a whole bunch of elementary matrices, and I multiply A by them one after the other, then the determinant of the resulting thing, B, is the determinant of ER, determinant of ER -1, all the way to the determinant of E1 times determinant of A. And this is just repeatedly using the previous result. B is ER times ER -1 times E1 times A. Now, ER is an elementary matrix that's being multiplied by these other things, and from what I just proved, I can peel that off and say that's the same as determinant of ER times the determinant of rest, and now I can keep that determinant of ER and peel off this next one, because that's also an elementary matrix. And by the result that I proved in the previous slide, I can say that the determinant of this mess is the determinant of the first one, which is an elementary matrix, times the determinant of the rest. And you can continue like that, and you will get that if you have a whole bunch of elementary matrices multiplied by a matrix, then you can separate them out in a product as we have shown. Now I'm ready to give you a slightly different version of actually the same proof that A is invertible if and only if the determinant of A is not 0. If A is invertible, A is a product of elementary matrices. The determinant of A is the product of those, and those all have non-zero determinants. So when you multiply them, you get non-zero. If A is not invertible, then A is a row equivalent to a matrix B with a row of zeros. That means you can start with B, do elementary row operations and get A. And instead of that, you can say you start with B and multiply by elementary matrices and you get A. And we know determinant of B is 0 because it's a matrix with a row of zeros. And so the determinant of A is now a product of those. And because determinant of B was 0, you get a 0. And so we have the second way of writing the same proof about why A is invertible if and only if the determinant of A is non-zero. Our main theorem in this lecture is that determinant of AB is determinant of A times determinant of B. We have already proved that if A is an n by n matrix and E is an elementary matrix, then the determinant of EA equals determinant of E times determinant of A. We want to bootstrap that and prove that this is true even if E is not an elementary matrix. Here's our theorem. A and B are two square matrices. We want to show that the determinant of AB is the same as determinant of A times determinant of B. And the proof is going to be in two cases. Either A is invertible or it's not. And we're going to do slightly different things in either case. If A is invertible, A is a product of elementary matrices. Again, you start with identity, do elementary row operations, you get A. That gives you A as a product of elementary matrices. And determinant of A is going to be the product of these determinants because of the fact that we have shown that when you multiply elementary matrices, you can separate the determinants. But what's the determinant of AB? The determinant of AB is going to be the determinant of EK through E1 times B because EK through E1 was A. But we know that we can separate those out. What we get is determinant of EK times the determinant of E1 times determinant of B. This first part is exactly what determinant of A is. And so I get that that's determinant of A times determinant of B. In the case where A is singular, when A is not invertible, singular means not invertible, then determinant of A is 0. We proved that earlier. And we also know that you can find elementary matrices that when you multiply by A, you get a matrix with a row of zeros. Now, C has a row of zeros, and when you multiply it by B, CB also gives you a row of zeros because that row of zeros, wherever it is, when you multiply it by the columns of B, you will always get zeros. C was EK through E1 times A, so I'm just multiplied both sides on the right by B. That shows that AB is row equivalent to CB. I started with AB, did elementary row operations, and I got CB. Now let's think about the determinant of A times determinant of B. Determinant of A is 0, so determinant of A times determinant of B is 0. Determinant of AB is also 0 because AB is row equivalent to CB, and CB has a row of zeros. If you have a matrix that's row equivalent to a matrix with row of zeros, its determinant is going to be 0. So in both cases, we have proved that the determinant of AB is the same as determinant of A times determinant of B. Now, as one particular example of how to use this, we will show that determinant of the inverse of A is 1 over the determinant of A. So let's say that A is some invertible n by n matrix, then that means that A times A inverse is identity. But we just proved that determinant of A times A inverse is going to be the determinant of A times determinant of A inverse. But determinant of A times A inverse is determinant of identity is 1. So these two numbers, whatever they are, they're multiplied to give you 1. So solving for the determinant of A inverse, you get 1 over the determinant of A. This is the end of this lecture. Like my video if you liked it. Subscribe to my channel if you like to be subjected to more math videos at the undergraduate level in your feed, and keep hydrated at all times.